Welcome to today's notes on transformations, finding equations based on the graphs. This is our final learning target of Unit 8, which means we are absolutely done with the notes for this unit after this. Learning target 14, write an equation for a given graph by writing it as a transformation or transformations of one of the 13 basic functions. By going through some of the basic steps we have to put it all together. So now that we have talked about the 13 basic functions and we've talked about what it means to transform them, we are now going to be able to look at a graph, identify transformations, and come up with the equation for that graph. Here are a few steps to help guide you through the process. First step. The first step is to identify which of the 13 basic functions was the starting graph. You can do this by looking at the general shape of the curve and relating it back to one of our 13 basic. Step 2. Make a list of the changes that occurred to get from the basic graph to the new graph. So now that we've talked about transformations, make sure you look for all of them, including changes in asymptotes, changes in intercepts, x and y, changes in steepness, did it get more or less steep, and reflections. Make sure you're looking for all of those things. Make yourself a list of all of those changes and then try to relate them to what that would mean for the equation. So you use your list, you put together an equation, and finally you're going to check your new equation by graphing it. If your final graph does not match the graph that you are looking at, you know that somewhere you went wrong. So you can go back and check your work and see what you need to fix to make that equation match the original. Okay, to start, we're just going to start by looking at equations and remembering what the pieces are. So this is just putting it together. This is an absolute review, so if you feel like you know this very well, you can go ahead and skip ahead. So identify which of the 13 basic functions is the starting graph. Identify how it can be transformed into the graph of the new equation. Well, the first thing I notice about this first one is that it has an e to the x as part of the equation. There is no fraction, so I know this isn't the logistic function. So I'm going to say that the original function is y equals e to the x. Identify the original function, we want to identify the transformations that have occurred to it. What I first see is the 9 out front. Any number that is a coefficient to your function is a multiplier. So that's going to be a vertical stretch times that number. So a vertical stretch times 9. Next thing I notice is that x is being subtracted by 2. That would technically be considered in the party, if you're in those terms. That would be in the party of x minus 2. So when you subtract from x, it's the same thing as moving right. So this function will move right 2. And the final piece of the puzzle is the plus 1 at the end, and since it comes at the very end and not part of the function itself, it's going to move the function up 1. Example 2 pretty clearly came from the original function, absolute value of x. There are 3 things that has happened to that. You've got the 2 out front, the negative inside, and the 3 at the very end. The 2 out front is going to represent a vertical stretch times 2. The negative inside is going to be a reflection. You do have to remember your reflections in the party correspond to reflections over the y-axis. And it's because it's backwards. In the party, with the x, it's backwards. It's not going to affect the x, it's going to affect the y-axis. And the very last thing, the plus 3 at the end, is going to move the function up 3. Third and final example of these, I know that you see 5 in your notes, but 4 and 5 will become clickers. It's probably the most difficult to see the general shape of, and it does come from the original function, y equals 1 over x. There are 3 things that have changed about that. The 8 at the top, the minus 4 at the bottom, and the plus 2 at the very end. The first thing I want to talk about is the 8 at the top. That's going to reflect, or that will be a vertical stretch times 8. Think about multiplying that 1 on the top by an 8. Okay, the second thing that's happening is the minus 4 that's technically in that party with the x in the denominator. Since it's in the party, everything is opposite. That's going to move the function right 4. And the plus 2 at the very end is going to move the function up 2. So we've got 3 different steps. Now that we've reviewed how we look at it from an equation, let's review how we can find it based on a graph. Okay, so these are our steps from the beginning, these 4 steps. First step is to identify which of the 13 basic functions you have. Hopefully by now, having done the 13 basic in Unit 7 and learned about them again in Unit 8, you're able to recognize that this is coming from the graph of y equals x squared. Y equals x squared normally has a vertex at 0, 0. If you plugged in a 1, you would get out a 1. If you plugged in a 2, you would get out a 4, etc. And this would be a parabola that was symmetric about the y-axis. What I first notice is that my vertex has now moved left 1 and down 1 from 0, 0 to negative 1, negative 1. So I know that I have at least 2 things happening in this graph. That vertex would normally, from the vertex, have gone over 1, up 1 if you squared. Our new vertex here does not go over 1, up 1. It goes over 1, up 3. So I have changed from that smaller piece to this larger piece. Okay? So my vertical stretch, instead of being times 1, is now 3 times larger than what it had been. So a vertical stretch times 3. It appears that those are the only changes because it is still opening upward, so there's been no reflection. If you reflected over the y-axis, it still would have looked the same way. If you reflected over the x-axis, that's when you would have had it opening downward. So these 3 are our 3 transformations. Put it together into the equation. Vertical stretches are out front of the equation. Anything that moves left or right goes in the party with x. So if I want to move left 1, I need to add 1 to the x in the party, and then to move down 1, I need to subtract 1 at the end. So I have y equals 3 times x plus 1 squared minus 1 as my guess. My final step is to check my equation to make sure I was right. Go ahead and plug that into your y equals. I have done the same. What I end up with is a graph that looks like this. I've turned on the grid on my calculator so that you can kind of see the same thing as what we had graphed originally. You'll see I've plugged in the formula and I've traced to 0, 2, which is the point that it gave us on the graph, and you can see the vertex at negative 1, negative 1. So we have confirmed that our equation is the correct equation. Next example. So in number 7, we see a curve that has a very limited range, but is not the waves that we're used to seeing in sine and cosine. So hopefully you can recognize that this is the basic function y equals 1 over 1 plus e to the negative x, that logistic function. The logistic function normally only goes from 0 to 1 and crosses at an upward angle above that axis. So we have to figure out all of the changes that have occurred to it. The first thing I notice is that it's been reflected across the x-axis. The second thing I see is that that point where it crossed at its midline is still on the y-axis, which means it has not been shifted left or right at all. The range used to be from 0 to 1. The range is now from negative 2 to 0, which means it is twice the range, which means that there is a vertical stretch times 2. think that those should be the only two changes that we have to make because it should look exactly the same. So our new equation, if we stretch by 2, that would be a multiplier. That's going to make the 1 on top of 2. And reflecting over the x-axis is going to make the whole function negative. Now e is still to the negative x. Graph this to check to make sure it works. Again, I've turned on the grid. The graph of our function should match the graph of what we were given, and sure enough it does. 0, negative 1, you see traced here is the point, 0, negative 1, that was reflected on the original graph. We only have one more example to go, and then the last one will be a clicker. Number 8, you see this graph. There are 3 graphs that can be commonly confused of the 13 basic functions. Y equals e to the x, natural log of x, and the square root of x are the 3 that commonly are mistaken. The key to knowing the difference between them is knowing that e to the x and natural log of x have both sides that continue to go toward one direction. So we are reaching an asymptote here at y equals 0 or an asymptote here at x equals 0 for e to the x and natural log of x. The square root of x has a starting point and then only continues in one direction. So as I look at this curve, I notice that it has this starting point and it no longer continues downward like natural log of x would have done. So I'm going to determine that my original function is y equals the square root of x. Okay, the first thing I notice is that the vertex, or the minimum point, which is normally at 0, 0, is now at 2, 0. So it has moved over right 2. Second thing I notice is when I plug into a square root, the square root of 1 would have been 1. Now when I plug in the square root of 1, I get out 1, 2, 3, 4. Over 1 now goes up 4. Over 1 used to go up 1. What that means is vertically I have stretched times 4. I know that it's not, not 3, 4. I know that it's not a translation because that minimum point has not moved up or down at all. So it has to be a stretch. Vertical stretch times 4. Okay, put those two things together. You're going to have y equals, to multiply by 4 you need a 4 out front. Right 2 goes in the crazy party with x and will be reflected as subtraction. So 4 times x minus 2. Take a second and graph it in your calculator. You should get a graph that looks the same as what we were originally given. You have the point at 2, 0, just like our starting point. And if you look at 3, 1, 2, 3, 4, you have a point just like here at 3, 4. That's all the examples for today. This was putting it all together and is the final piece of our unit. Hooray, you're done.